Newton's first law of motion. Put a smooth cardboard on a horizontal table. Keep a heavy book on it. Pull the cardboard suddenly in a horizontal direction. What do you observe? The book will fall on the table. The inertia of the book resists the change of its initial state, which is stationary. As a result, the book does not move with the cardboard and falls on the table because of gravity. Every inanimate body continues in its state of rest or of uniform motion in a straight line unless an external unbalanced force acts on it. This is known as Newton's first law of motion. The state of rest or the state of uniform motion is because various external forces cancel out to give zero net resultant force. Newton's first law explains inertia, that is, inability of a body to change the state of motion by itself. It also explains force, which changes or tends to change the state of rest or of uniform motion of a body in a straight line. All the examples of inertia are examples of Newton's first law of motion. Newton's second law of motion. Activity. If you ask your friend to drop a plastic ball and a rubber ball of the same size from the terrace, you can catch the plastic ball easily because its mass is less than the rubber ball. The force required to stop a moving body is directly proportional to its mass. Now, ask your friend to throw a ball very slowly and try to catch it yourself. And ask him to throw the same ball with very large velocity and try to catch it. It will be easy to catch the ball that is thrown slowly because it has lesser velocity. Mass or velocity alone are not responsible to produce the effect of force. There appears to exist some property that combines the mass and velocity of the object. Newton introduced this property as momentum. Momentum measures the motion content of an object. Momentum is defined as the total quantity of motion contained in the same body is called momentum. Mathematically, it is measured as the product of mass of body and its velocity. P is equal to m multiplied by v. Momentum has both magnitude and direction. Its direction is the same as that of velocity. SI unit of momentum is kilogram meters per second and CGS unit is gram centimeters per second. As velocity of an object changes due to application of force on it, the force also produces change in momentum. The force necessary to change the momentum of an object depends upon the rate at which momentum changes. Newton's second law explains about change in momentum. The rate of change of momentum is directly proportional to the impressed force and takes place in the direction in which the force acts. Let a body of mass m, moving with velocity u, be subjected to force F acting in the direction of motion. Suppose v is velocity of body after time t. The total initial momentum of a body is mu and final momentum is mv after time t. So rate of change of momentum is equal to change in momentum divided by time. Therefore, rate of change of momentum is mv minus mu, the whole divided by t. After taking m common, we have the rate of change of momentum is equal to m multiplied by the difference of v and u, the whole divided by t. Therefore, the rate of change of momentum is equal to m multiplied by a. Hence, by Newton's second law of motion, rate of change of momentum is directly proportional to F. As the rate of change of momentum is equal to m into a, we have m into a is directly proportional to F. Thus, we have F is equal to k multiplied by m multiplied by a, where k is equal to 1, a constant. In the SI system, Newton is unit of force. 1 Newton is defined as the force which causes a mass of 1 kilogram to move with an acceleration of 1 meter per second squared is called 1 Newton force. 1 N is equal to 1 kilogram multiplied by 1 meter per second squared. In the CGS system, dyne is unit of force. 1 dyne is defined as the force which causes a mass of 1 gram to move with an acceleration of 1 centimeter per second squared is called 1 dyne force. 1 dyne is equal to 1 gram multiplied by 1 centimeter per second squared. In a high jump athletic event, the athletes are made to fall on a sand bed. This is to increase the time of the athlete's fall after making the jump. This decreases the rate of change of momentum and hence the force on the athlete. This reduces the risk of injury to the athlete. Let us consider two bodies of different masses initially at rest. Suppose a fixed force is applied for certain interval of time on two bodies. The lighter body picks up greater speed than the heavier object. But at the end of the time interval, each body acquires the same momentum. Therefore, the same force for the same time causes the same change in momentum for different bodies. It shows that force is directly proportional to change in momentum at fixed time for different bodies having different masses.